Hmm. Okay. Hmm. We'll take a minute also so that people will join in.
Sir,
Yeah, tell me.
do we like batch C and D? Do we
Huh?
also have to submit
No, no.
assignment
Batch C
in?
and D is with Professor Johnson, sir, right?
Yeah, yeah.
So
But
whatever he
in the
will tell, accordingly, we will follow the instructions by Johnson, sir.
okay,
Okay. So and still, batch C and D should join. What is that? The MD lab course in Moodle. The
yes, sir.
requirement
That
is
is what
that
I was asking.
no, no, no. You should join not for the submission of the assignments. Okay, you will follow the instructions of Johnson sir for that purpose. Why I'm telling you to join is that because in maybe at the month end there may be online test, right? At this month end, August end,
Mhm.
or in first week of September there may be online test or first what do you say unit test or internal assessment IA1. So for that I will be conducting IA1 on that platform. Therefore, I want all of you to join MD2 lab course in 7th semester for A division. Fine.
Okay.
Yep. Okay. So hope that all of you have joined here. So shall we continue from where we left in the previous meeting?
Yes, sir. Yes, sir.
Yeah, yeah. I'm just admitting some other people. Okay. Well, so I'll share my screen here, and Justin, you need to mute yourself. Hmm. So let me start share screen. Okay, here we are. Fine. Where to stop this? Okay. Okay. So I was explaining about the how do we incorporate dynamic load in the design, which is actually on the basis of static loading. PT, there is tangential load coming on to one tooth, which is in mesh with other tooth on the pinion or gear, right? That is a static load. But the gears are in motion, and there is a dynamic load because of so many reasons which I mentioned, right? So Barnes performed one experiment, and wherein he found out a velocity factor CV as a ratio of PD upon or FD upon FS. So where FD is dynamic load and FT is tangential load. So here you can see on page number 8.50 there is the equation FD is equal to FT into CV. So you can write CV is equal to FD upon FT. Okay, so that way they actually come up with expression empirical relations for velocity factor CV, and there are three different or four actually different relations for different conditions. So for velocity, pitch line velocity less than 10 meter per second and commercially cut wheels, we can make use of this equation here. carefully cut wheels, then precision wheels, we can make use of these equations. And if in case of non-metallic gears, we can make use of this equation. But we are not related to non-metallic, so it's not considered, at least for in our case. Well, so we can find out what is velocity factor from these relations, and again we don't know what is the condition, what is whether it is commercially cut, carefully cut, or precision wheels. These things, as a designer, the designer has to make use of his past experience and intuition for a given application to come up with what is the magnitude of CV, or which formula for CV initially he is going to consider, or he or she is going to consider in the design. Fine. So once you know, or you assume about the what is the expression for CV, you find out CV, and on the basis of CV, by making use of Barth equation, we can find out dynamic load. Okay, dynamic load FD is equal to sorry, wait a minute. Yeah. So FD is equal to FT into CV, wherein FT is tangential load, which you can find out on the basis of um torsional moment MT, because FT is applied at a FT is applied tangentially at the pitch circle diameter. Okay, so FT into diameter by 2, that is the radius of that gear pitch circle, is actually torsional moment. So from that you can find out FT. Okay, so once you know FT, once you know CV, you can find out FD. And the condition to for design is that the design will be safe if Fs is greater than Fd. This condition we need to consider. Fs is greater than Fd. Fine. So if it is satisfied, that's fine. It doesn't satisfy this condition, then we will have to go back to our design. You can make in changes of the CV, there is velocity factor, and check whether it is having effect, or does it affect as far as design is concerned. If it is coming safe, that's fine. Otherwise, you'll have to go back and change your module. Okay, so we estimate module on the basis of beam strength, but you will have to increase the module by 30 to 50%, and then select next preferred module from the data book. Okay, so then recalculate once again, and you will essentially find that most of the cases, once you increase the module, design will be safe. Okay, so this is on the basis of Barth equation. Now, sometimes in the examination, they may ask you to find out dynamic load using Buckingham equation. Fine. So I had kept this Buckingham equation for next stage, that is helical gears. So therefore, I have not discussed about that. But here, suppose it is mentioned in this stage also, you need to find out dynamic load by making use of Buckingham equation. Then make use of this equation here. Buckingham dynamic load FD is equal to FT plus this bracket. And I think we have discussed about this. So you can make use of this. But if it is not mentioned, obviously we will go for easy way out. We will consider this equation FD is equal to FT into CV, which is on the page number 8.50. Fine. Any difficulty till now? It shouldn't be, because it's a pretty straightforward procedure. Only thing is that we need to collect so many things together and go step by step. That's it. Well, so once you prove that beam strength is greater than the dynamic load, your design is safe in, or the same static loading for beam strength. But gear also fails because of the surface fatigue, or due to contact stress. Okay, so for that we find out what is the wear strength, and then we have sufficient discussion on that, how to find out wear strength of a tooth which is in mesh with another tooth. So I will go to the PPT now. This is step number 4. We have considered checking of dynamic load for beam strength. Okay, so once you complete this, now we'll go to step number 5. Okay, so here we are, right? Check design for wear strength. Now, before we check the design for wear strength, we should know what is the surface stress or contact compressive stress for that material which we have selected. Excuse me. Well, And that's what we did last time. We selected for whatever material we have selected, we found out the surface design surface stress or design contact compressive stress sigma c, and the whole procedure I have explained from the data book. Now there is another one empirical relation many times professors suggest in the university. It is, I think, 0.28 into bracket BHN's average BHN minus 70. Okay, that is that equation is given in AGMA, that is American Gear Manufacturers Association, AGMA. Some people call it AGMA. Okay, so AGMA has given one empirical relation to find out sigma c. Okay, so that is sometimes people use that also. That is fine, but there is no need to remember that. There is a pretty straightforward procedure mentioned in the data book to find out what is sigma c. So we'll find out sigma c from page number 8.16. Is that fine? Well, then once you know this sigma c, we are finding E1 and E2 for the material selected. We find out K, we find out Q, and all those things are required for finding what is the wear strength. Okay, so this is what we are till now we have discussed. Any difficulty till now? Especially those who had lost the track of what we did till now. Is it clear now to all of you?
Yes, sir.
Okay, so as I mentioned, I want you to maintain notebook, separate notebook for this. Whenever I tell you to find out some value, do that, because then and there your doubts will be clear. Many times the reason is that in data book the units are in different system, and we generally are familiar with SI systems. Okay, so sometimes you may come confused with the units of the parameters in that equation. Like for example, you will consider B in millimeter and module in centimeters. That may happen. Or you consider all the parameters in proper units, but one parameter is not in that particular expected units. So these type of mistakes do happen if you are not having practice of doing it. Okay. Okay, you may feel that I will do when at the time of examination and all those. That's fine, and you can do it. There is no difficulty. But why not to do here and here itself, so that we can have sufficient practice of it. Okay, which will reduce your probability of committing mistakes during examination. Fine. So we have found out ratio factor Q today, and we have found out what is the load stress factor K. And on the basis of that, I have asked you to find out what is the wear strength of the gear tooth. For the equation of wear strength, we'll go to data book. Here it is. Okay, Fw is equal to, just write down this equation. Fw is equal to D1Q KB. I'll just increase the size of this. Okay, so here it is. Fw is equal to D1 Q K into B. So we know Q, we know K, we know B, we know D1. So find out Fw and let me know what is magnitude of Fw.
302.8625.
Okay, 302 point whatever 82 whatever. I will just check whether, well, here I have written determine wear strength of the gear tooth Fw. It is same formula D1 Q K B. Okay, so I will run this portion of the code and we'll just cross verify what are your answers. Again, I have written answer in Newton also, as I mentioned some time back. It's good practice to express the important quantities in SI units also, though we are finding in MKS or this CGS system. Well, I will run this. Yeah, it is FW 6513.6. What is how so much difference? No, no, there may be mistake in my calculation now. But I think I might have considered B in terms of. Let me check the code. Okay, so what I'll do, I will rerun the code till this 185 completely, so that there is no mistake in this calculations. Okay, so I have cleared the data from there, so I will put a breakpoint here. Well, and we will now run the code till this point. Okay, so it's run. Yeah, it is 303.219. So yours was 302.8 something, no?
Yes, sir.
So they are pretty close. Here in code, it considers accurate values. Okay, so in your calculator, you are doing the same thing, no? But this may be because of some approximation or rounding off somewhere.
Yes, sir. I rounded off Q.
So that may be that is fine. There is no difficulty. Well, as I mentioned, the answers for design will vary from your assumptions. Now here we are having uniformity for the initial assumptions and materials and corresponding values. Therefore, it should be very close enough. Okay, and we are doing it just for say for sake of cross verifying, so that we are on the same page. Okay, so this is okay. FW is equal to 3.303.219 kgf, which is 3032.19 Newton. Fine. And what is your value of FD design value? It is 4109. Right?
Yes, sir. Newton.
Okay, it is in Newton or 410 kgf, which is here.
Yes, yes.
So therefore, in wear strength also, because FW is greater than, oh no, wait a minute, FW is less than FD. So design should
Yes, sir.
fail. So design fails here. Okay, let me see whether my code gives correct result here. I will run this portion of the code. Okay, so let's see what happens. Code also should mention the same thing, no? Oh, what happened here? Oh, what I did.
Sir,
Okay.
there is a plus
No,
sign.
yeah, no, yeah. It was actually expanded and what is it? Contracted something.
Yes,
Okay.
sir.
Anyways, let's say my code says whether it is safe or unsafe. Yeah, design is not safe. Okay. Okay. So when you write this step, you should clearly write since FW is less than FD, design is not safe. Yeah, so those who are honestly disturbing, please unmute yourself. Mute yourself. Okay, so design is not safe. So then what we should do now? As I mentioned, actually we had a discussion regarding CV some time back, right? And therein we have already considered CV for precision gears. So we cannot make changes there. So we will go back to the module stage and increase the module by 30 to
Select bigger
50%.
module.
Huh?
Sir, bigger module. Na?
What is that?
Hello.
I'm not able to hear you properly. What is that? Can you repeat it?
Hello.
Yeah.
Sir, the value of face width is 26 mm. Na?
No, 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 no.
So if
See,
we
listen.
approximate it,
Wait a minute. Who's this?
Sagar.
Sagar Save.
Yeah.
Yeah, Sagar. Right. You are correct. The value of B initially we had considered 26 or so because that was on the basis of module calculation. Accurate calculation is 2.6 or so. Okay, but then
Yeah.
in design data book we selected the module which is close to 2.6 and preferred module it comes out to be 3
Okay.
centimeter.
Okay.
Oh, sorry, 3 millimeter. Okay,
Okay.
so on the basis of that,
Okay. Okay.
okay, fine. Okay, now though we have considered module as 3, well, I don't know why people are unnecessarily disturbing. Okay, that's fine, because you're hiding behind the screen. Okay, so and I don't want to spend my time to find out who is doing this, which is possible. Okay, but be careful about these things. You are in third year of engineering. Huh? So, anyways, so now what we'll do, we will increase the module by 30% or so, 30% to 50%. Okay, and select, or straight away we will select next stage of the from the preferred series of the module. Okay, so we'll go to preferred series of the module. Okay, so here it is. Well, it is in gears. Yeah, so I have instructed that you should not disturb, therefore there is more disturbance. So that is understood. It is natural human tendency. So if you are told something not to do, it's like that I will do it. Okay, so keep on doing that. No problem. Okay, so I will not attend to that these things now. And if there is much disturbance, that's fine. I can't do help in that. Okay. So we will go to basic rack here. Yeah, so here we will find out. See, here it is preferred series of the module on page number 8.2. Okay, and here we had considered 3 as the module, which we'll consider now 4. Next step is to next stage. Okay, so to consider module as 4 and redo the calculations and tell me whether it is coming safe or not. Now here there is no need to calculate the beam strength. Okay, because there is a failure of the gear tooth in wear strength. Okay, so therefore we will just find out what is the wear strength of this on the basis of increase module to 4, and accordingly if there is a requirement of changing the FD, we will do that and see whether the design is safe in this or not. Okay, so find out FW and FD with increased module as 4 and tell me what is the answer. Okay, so I'll wait till then. Well, so when you are ready for this, just raise your hand. I will unmute all of you. So take a 1 or 2 minutes. So are you ready with the answer? Okay. Okay, so okay, so if you have calculated, let me know what is the value of FW and FD. Okay, so I'll save the chart now as an attendance. Everybody has marked P over there. Acha, so you are marking once again. Okay, I will save the chat now. Fine. Yeah, tell me answer. What is FW and FS? FD.
Sir, FW is coming as 539.06 kgf.
FW is coming at 539.06 kgf. And what about PD or FD?
Sir, still finding.
It was 40 something, no? 402. Yeah, it was 410, 410.99. Okay, so we have changed the module, so diameter will change.
308.226.
Okay, so 308.224. That is FD. Right. So let me run the code again. I will increase the module to 4 and rerun this part, this code till this point. Okay, so I will just run till this point. Okay, so I'll mark this as and I will remove this breakpoint from here. Okay, so I'm going to increase module where it was. Yeah. So here if you see line number 109, M1 is initially 0.3. It is 3 millimeters, but I am considering 0.3 because we are calculating in centimeters. So I'll change it to 0.4 now because I have already. Now again there is a message saying that 10 minutes to go. Okay, so we will do similar way. Okay, we will rejoin the meeting immediately. It closes it. Okay, and we will have till 5 o'clock today. Lecture till 5 o'clock. Is that fine? Okay. So I will change this here to zero point 0.4. That is 4 millimeters. And okay, so I will run the code again till the required point. Fine. So let me see whether our breakpoint is still there. Yes, breakpoint is there, so it will run till this point. Yeah. So let us check the changes here. Yeah, FW, check the value of FW. It is 539.50056 kgf. Are you getting the same value?
Yes, sir. Same value.
Yes, sir.
Yeah, and let me see. Now you can see the message is also design is safe here.
Yes, sir.
Okay, so this is what we will do in the examination also. Okay, now many times in the examination, if you are what to say, not able to get the design safe answer again and again, then it will kill your time actually, and in that what to say tension of the examination, you will commit some other mistakes because of that. So when you are solving this problem, you always keep in mind, if I consider value of CV, what value of module, then it will be safe. Okay, so here I have mentioned that we need to increase the module by 30%, but I have seen that people straight away tell to increase module by what is it, 2 times. If it is 3, they will straight away make it to 6. That is also seen. Okay, so that is a very conservative way of doing it, because as you increase the module, size of the gears will increase, cost will increase. Therefore, you will have to be very careful about this. Okay, but in examination, sometimes just to save time, you can do that. Some assessor may reduce some marks, but he will not reduce all the marks. Okay, so that keeping in that in mind, we will go ahead. Okay, so in maybe 7 minutes, we are going to close this meeting, and after that, you will rejoin again. Okay, so I will just see on the slide. We have checked for this design, check design for wear strength. We have now checked it for beam strength as well as the wear strength. So what is next in this? We'll see. Okay, so this wear strength, we have discussed about this, how to find out sigma C. We have discussed about this. Now next step is we need to collect all the dimensions of the gears which we have designed. Okay, so see, prepare this table now, wherein you will actually collect all the parameters. You should prepare in this like this in your answer book. Okay, so you will have say 4 columns. What is the material? Or if you don't mention this, that's fine. Okay, so there is, you can just mention what is the nomenclature for that. That's also okay. But if you write it in this way, that will be pretty clear what you are mentioning there. Well, so you will collect all the dimensions of the pinion and gear here in this table. Okay, so initially we will mention about the material. I have not mentioned here in material. Okay, so you'll once again write what is the material you have selected here. Like this is like a sort of summary of the all the dimensions of the gears. Okay, it becomes easier for us to see what are the total overall dimensions. Okay, so you will mention about number of kits Z here, Z1 and Z2. Then you will mention about the module. Module is same for both pinion and gear, so I have mentioned only one this thing. But in exam you can write twice. There is no difficulty, or you can write only once. It's up to you. Phase width will be also same, so that is single value. Pitch circle diameters D1 and D2. So D1 for pinion, D2 for gear. Rohan, you want to say something? Fine. Addendum again. Now after this, because till now we have found out in your calculations. After this, all these parameters you will collect from PHG 8.2 and 8.22. Okay, on page number 8.22, the relations for all these parameters are given. So straight away you will collect from there and you will write the values in front of it. Okay. So addendum, dedendum, clearance and tooth thickness and fillet radius, all these parameters will be having same value for pinion as well as gear, because that depends on module itself. Okay, so you can see all these relations, it depends on module itself. Only thing is that there will be different tip diameter for pinion and gear and different root diameter for pinion and gear because of change in PCD D1 and D2. Okay, so I'll just show you page number 8.2 and 8.22 from data book. So we are on page number 8.18. I'll go initially to 8.2. So this is 8.2 is on basic rack. So here you can see the basic rack for the pinion and gear is shown for the spur gear. I'll just enlarge this. Okay, so from here also you can find out actually what are the dimensions. Okay, this is M, total depth is 2.5 times M, this clearance is 0.25 M. Okay, but then here you can draw this diagram and don't look for the dimensions from this diagram. No, you directly go to page number 8.22, but it is essential to draw this diagram. Excuse me. Now I'll go to page number 8.22. So I think it should be in gear geometry. Acha, it went to page number. Okay, so I'll just scroll down. Yeah, so we are on page number 8.21. Sorry, we need to go to page number 8.22. So here it is, 8.22. So on this page, all these gear overall dimensions are given for the spur as well as helical gears. You can see here. Well, meeting will end in 2 minutes. Okay, so rejoin after this. You can see here all the dimensions are mentioned. Center distance is also given. Oh, where is my cursor? Yeah. So center distance is here. Then there is no need to mention all these factors. Okay, so whatever factor I have tabulated on the slide, only these things you will consider. Okay, so tip diameter is this dA1 Z1 plus twice FO into M. Okay, what is FO? FO is equal to 1. In special cases, FO is 0.8. So FO is 1. Okay, so Z1 plus twice FO, which is 1. So 2 into M. Okay, so M into Z plus twice M. So M into Z1 is pitch circle diameter D1 plus twice M. Okay, that's what I have written for tip diameter in the slide. Okay, see PCD, that is D1 M1 into Z1 plus twice M. Right. So like this you can find out all these parameters which are listed on this slide from the page number 8.22 here. Okay, root diameter is also mentioned here. So now I will end this meeting. So you'll rejoin, and while rejoining you simultaneously do the calculations of this table also, and then we will see and cross verify the answers. Okay, so please rejoin. I'm ending this meeting now. Is that fine?
Yes, sir.
Yeah, yeah.